I guess we might as well get started. Welcome back from afternoon tea. I'm sure you all had a wonderful one. I ducked down and had a couple of those nice chocolate eclairs myself. This afternoon I'd like to welcome Stuart Smith. He was a major part of Australia's first student-run internet groups at high school before he going to Monash University. And in fact, he was a bit of a stir at Monash as well, because while he was there, I believe he organised about a half a dozen or more Linux install days and quite a few beerbecues.
Yeah.
Beery barbecues,
yeah,
something
beer
like
for
that.
Me.
Yeah. Ball or two. And he spent the best part of 3 years on the executive of the School of Computer Science and Software Engineering Student Club there, after which he was given an honorary life membership.
Did I write this bio?
I think you might have.
Oh, wow. I'm learning things. Shit.
Okay. Towards the end of his third year, he began to redesign the membership database, which has since turned into what LA is using now.
Which should not be taken as an indication of the quality of code I write.
He's since completed an honours in computer science with his thesis topic on an object store for the walnut kernel. And he was heavily involved in the migration from True64 to BSD.
For Yo-Yo. I didn't write that. Well, yeah. Yeah,
And consequently earned the right to cry in a corner of every room when True64 was mentioned. He's a software engineer working for MySQL AB, which he tells me means proprietary limited or something to that effect, on the MySQL cluster. And he's spoken at a large number of conferences. And I would like you to really make him welcome at our conference today, Stuart Smith.
Right, thank you. So I'm talking about Eat My Data, how everybody gets file I/O wrong. And the idea for this talk came amongst, shall we say, a buggy laptop driver that kept making my system crash, and I noticed all this data was getting lost. And I do now actually carry around a current file system dump, and so when some application screws up, I can just restore at conferences, and I learnt that the hard way. So hopefully I shall encourage you to do a bunch of seemingly obvious things in your code to make sure that the user has a good idea of data consistency and other such things. So a bit about my day job. I work on MySQL cluster, which is a high availability, shared nothing clustered database with some real-time properties. So it's a real simple software system, and we never have any bugs. No, it runs pretty well, really reliable. A lot of telcos use it, so it's pretty neat and stuff. A bit of an overview of what I'm going to talk about. There are a lot of common mistakes that software programmers make that can lead to data being eaten. There's mistakes by the application programmer. These are by far and more the most common. You'll find a lot of bugs in at like application level where it's just one or two more syscalls and that data would have been safe. The library programmer, I'll make it easy for the application programmer, but instead get it wrong, which requires workarounds in the application. Fun. And the kernel programmer by perhaps making our lives sort of back in user space just that little bit trickier. I'm going to mostly concentrate on Linux, and I'm going to tell you like a war story from another platform, which is a good warning to say that just because it compiles and runs doesn't mean your data is like any safe at all. And I'm going to ignore Windows because it's irrelevant. So in the beginning, all I/O was synchronous. You called like write and it suddenly ended up on disk. And that was like simple life back in the day, but like turns out that this sucks for performance when you have like more than one process running as well. So that no longer happens, so don't assume it. A world without failure doesn't exist. Computers crash, power goes out, batteries go flat, someone kicks the cord out of the machine, and suspend works but resume doesn't. You know, just because Matt Garrett can fix your laptop doesn't mean you should rely on that for data integrity. When the data is important, and this is an important thing to distinguish, what data is and isn't important, live in the world of failure. Assume nothing will ever succeed. And that's a bit of a mind switch to make. Check every error code. Consider every error code unchecked a bug. So, a question to ask yourself is data consistency. In the event of failure, what state can I expect my data to be in? The user has expectations. If the power goes out while I'm typing a word processing document, I expect that the last version I hit save on is there when I reboot my machine. If it's not, I hit it, swear at it loudly, throw it out the window, and go back to writing on paper, which I actually did in high school. If there isn't an explicit save, so a bunch of applications now are doing like saving things in the background, like RSS feed readers with the feed list, instant messenger logs. You don't like save them all the time, they're just written back to the disk. With applications like this, often it's just a recent version is okay. Not acceptable is when I hit save, why is none of my work there? You get antsy with this at about 4 a.m. when something's due at 8 o'clock in the morning. Why have all my instant messenger logs suddenly disappeared? Or one that I hit, why have all my saved passwords disappeared? I can't log into anything anymore. So, you may have heard of the thing called databases. It's been around for a little while. They have this thing called ACID, where D is for durability. And you have transactions, where a committed transaction survives failure. This isn't necessarily power failure or whatever, it may be node failure in a cluster, but you have this different isolation levels for data consistency, like across different transactions. But you've got some very well-known consistency issues that lots of people still get wrong. So different engines have different properties. Some do have more of D than others, and have different things. So if you're doing databases, you also have to worry about data consistency. A bank has rather stringent data consistency requirements. Maybe logs for a web server doesn't. So have a think about that. Databases are good at lots of small objects. Rows are typically rather small, and databases are written to accommodate this. They're okay at larger objects, and I'd like to give you a little history lesson. Blobs are named after The Blob, the film, not binary large objects. And give Jim Starkey a couple of beers and I'll explain it, but he's not here, so send them to his house. They're accessed by a variety of ways. So you have different indexes, you can do index operations, which puts it in use for some problems. So there is an easy solution for data consistency. Whack it all in a database and use transactions, and it gives you data consistency and you don't have to worry about it. And we'll talk about this a bit later. It's a good way to cheat and get around some of the bugs. Revelation number 1. Databases are not file systems. Storing every single bit of data in a database probably isn't a good idea. And the converse of this is to realize that file systems aren't databases. Sometimes you probably do actually want to use a database and not think, I know, we'll put each row like in a file and then we'll use symlinks to index them. And any like coincidence that I may be writing an engine for MySQL that does that is just only to prove how crackful it is. Revelation number 3 is a database has different consistency semantics than a file system, right? So databases have this idea of this is a transaction and commit means this and all that kind of stuff. And when you write stuff, you have this idea of what happens. File systems tend to be a little bit more relaxed. Very interesting talking to database people suddenly about file systems. And they go, so what happens in this failure mode? Whatever was on disk. Oh, that makes it easier. So, eat my data. Where is the data that could be eaten? Well, an application could crash. So, whatever is in its memory that it hasn't written to disk yet will be gone. So you can have like a random buffer. You malloc a buffer and you modify your word processor document in this. And if you haven't hit save, well, it goes away. You can have a library buffer, like libc, where you've got I/O, where you like write character at a time. It's probably not going to output a character at a time to stand it out, for example. It's buffered. So if your application crashes again, this data's gone. You can have like a page of buffer cache in the operating system. So it's got some dirty pages in memory that it hasn't decided to flush out. And if your system crashes, then these are lost. But if the application does, then they'll still make disk. And your disk can fail. This is loss of data, and this is the idea of having backups, which is a novel approach. But an interesting thing is that some data sets are too big for backups. Once you get up to about a certain number of terabytes and petabytes, it becomes a really hard problem to back it up or even restore. But good luck with that. Get enough money. So, what can you use for the data flow here? So an application can call like fwrite, fprintf, and friends and do all that stuff. A library can call like fwrite for like write, libc will do that, or your application may do it directly. And the OS buffer, so once you've got dirty pages out of the application, the operating system can either page it out, like periodically flushing, like 5, 30 seconds, 2 seconds, whatever. But an interesting thing is this thing called laptop mode, which has been circling around, which doesn't flush dirty pages to disk, because that requires spinning up the disk, which uses a bunch of power. So if you're running in this kind of mode to power save, you can have a lot of dirty data sitting around that isn't flushed to disk for a very long time. fsync, fdata sync, and sync do actually, at least in theory, flush things to disk, with caveats that we'll talk about in a sec that makes your life hell. We'll in fact be going through an implementation of fsync, POSIX compliant one, so it may hurt your brain, but it's remarkably simple. So let's have a look at some code for doing a simple application save to disk, right? So a user may hit save in a word processor or some application and expects this to be on disk. So let's grab a simple structure and then we'll sort of like open the file that we want to save, let's say important document, and fwrite it out. Where's the bug? Good answer! Brilliant, someone gets a cookie. So you don't close off the file, so we're probably going to not only like leak a little data structure there, but the buffers may not be flushed out, depending what it is. If you're doing like maybe a log, you may want to flush the buffers out so it hits at least the buffer the cache in the operating system. You may not care, but it's often a good idea, like where it goes. So well, let's close it off. What else might be the problem? Yeah, there's like lots of stuff, like no error checking. Did we actually open the file? Did we write the entire file? You know, hitting E no space halfway through it's going to be an interesting thing. Fclose, did we successfully close the file? So it turns out that you can get like E-enter on fclose. And then let's have a look at file system integrity. So metadata journaling is just that. Metadata only. No data is written to the journal, and the integrity of file system structures is assured, not the internals of files. Does anyone have a problem with this? Good. Understand it? Good on you. Right. Oh, there's bugs in every file system. That's why you have like fs check, and like your memory goes bad.
Check will always work on XFS though. I mean, I guess some people do like their files turning into directories randomly. But
So I'm not going to mention any other file systems that like putting, let's say, disk images in them and running fs check leads you to a place that does not have hugs and kittens. So there's always one thing that will work, mkfs, but let's not use that for like assuring file system integrity. So data journaling is nothing like a database transaction. So you'll see some file systems have data journaling. It's not like begin commit in a database, and don't think that and assume it, as some people have done. Atomic write isn't. It can half complete. A file system with atomic write, well, you can't rely on it being there because like everyone uses the same file system because it's the one true way, right? Shit, everyone does. Oh, that ruined that point. So everyone's running like XFS, great. So an atomic write in a file system is essentially useless because you can't guarantee it being there, and any application that does is instantly going to be buggy as soon as you mkfs with something else. So eat my data. Your machine crashes halfway through writing the file out. What do you have on disk? Nothing, half of V1 and half of V2. So this works really well for...
really lucky it crashed just before that fwrite and you've done a truncate that you haven't started. And you've got none of either.
Yeah, so if you're really lucky, you get like a 0-byte length file. If you're a bit more unlucky, you get this great like binary format file that like is interpreted complexly by a program, where you have half of it the old version, half of it the new version, and of course the blocks could be interspersed in all sorts of random order depending when it was flushed. So you end up with what we refer to as crap. Which, funnily enough, does not resemble your thesis that's due in 3 hours. So there's this old trick, write to a temporary file and rename. So who thinks this is the final solution, everything works if you do that? Raise a hand. Helps. True. You can catch any errors. No space halfway through writing the new version of the document, or you're getting longer. Guess what? The old file's still there. You use it and return an error. You don't rename one error. Don't write to a temporary file and rename if there's been an error. Because that's what happens. I come along, smack you around the head, and say, you bastard lost my data. So the idea is if we crash or have some kind of error during writing the temporary file, the user data is safe, or at least some version of the user data is safe. For example, the old, no more space, delete some stuff and do something. It's a really good way of finding bugs in software as well, to run out of inodes, run out of disk space, and then see how spectacularly your machine starts to shit itself and cry. So we may leave around a temp file if we crash. That's an okay failure mode. Extra data is better than no data, right? So let's implement it. Let's write to important document.temp. Let's do some error checking. Ignore fclose errors because we'll happily leak a file descriptor. Yay. And then we rename at the end. Anyone see a bug?
Fclose can return no space.
Yeah, that is a good thing to return. Tridge gets a cookie.
You didn't make a secure temporary file name.
This is what we call example code. We could have it all complete, and I'll actually implement, I'll put OpenOffice code up, the complete one of that, and we'll use that for the example, but we may be here for a little longer and, cry. So now's all good in the world, right? Apart from possibly checking the other errors on fclose, depending on the platform there.
Perhaps error checking on rename.
Error checking on rename. Yep.
Rename before you close it? No. Because how do you keep someone from doing something and when you close the rename?
You also have the problem with symlinks and hard links.
Yeah. So again, some people have glasses on. So we're going a bit of a general case. So all is good in the world. So a lot of people stop here, but there's a couple of other cases that isn't on the screen because it makes the text too small. And there's also a bunch of other little things that are a whole lot more subtle than the obvious ones. Close and rename do not imply sync. Yeah. So, close and rename do not imply sync. So, they make no guarantees on when or in what order changes hit the platter. It's quite possible, and often on a lot of systems, that metadata is flushed before data. If you have a lot of metadata operations going on, your file system may need to flush some stuff out of the journal before the data gets going out. So, data equals ordered mode on X3 writes data before metadata to try and sort of get away some crap application programs that don't know what they're doing. So other file systems are different. X3 ordered mode is the exception, not the rule. So applications that rely on this behavior was probably buggy. So data equals order. You write, close, rename. So you're probably going to get data from write, hit disk first, and then you're going to get the metadata running. Other systems, anything can happen. So let's flush, so we get the buffers out, and we fsync. Oddly enough, we check the error code. I heard one ooh. Everyone else is going, remember that. Yeah, I don't, because it's longer. No one ever checks the return of fclose.
NFS has got such a bad reputation. There's NFS that fails in that case. No one checks close.
And then we rename, of course, with error checking off the bottom of the screen. So a tale of libxml2. Has anyone ever used an application that uses XML? So anyone ever used GNOME? Yeah, or anything that uses dbus? Yeah, so you're using libxml2 and a bunch of your computer working relies on it doing some nice stuff. So the nice application developer saves time by using the libxml2 function to write data to disk. So grab this XML thing and write it to disk. Application developer writes it, Even does temp file and rename. They're being good. User loses data after crash. Nice application developer has to read through the source code to the library and work out what's going on and write a lovely workaround. So it turns this bit of code, and this is actually from LifeRay and dbus because it found it first, turns this into this, which you pass to libxml to. So thanks library developers for perhaps not giving an option to like save with sync. That would have been nice. And this is the actual little bit you're doing, fsyncing down there. So we're nearing nirvana. If we have any failure during writing, the previous saved copy is untouched and safe. So the user doesn't really get partial or no data. Except if you want to be portable. So on Linux, it just happens to be that fsync does actually like end up writing some stuff to disk and like returning back. Barring enabling of the write cache on disk drives, that's a good way to like end up without hugs and puppies. Although it can like increase your write performance. Especially if you're writing the same block lots of times. Geez, that's fast disk. So, don't enable write cache on disk drives if you like your data. On Mac OS X, which a bunch of people around here are using, not so much. So they, in their infinite wisdom, decided to make it even harder for application developers to get data safely on the platter. Let's look up POSIX. Let's go at the consequence. If the POSIX synchronized I/O is not defined, so there's a hash defined that turns out actually isn't there in even like Red Hat 8 and 9, if you want to be portable back to that, the wording relies heavily on the conformance document to tell the user what can be expected from the system. It is explicitly intended that a null implementation is permitted. It is explicitly intended that a null implementation is permitted. So, let's write a POSIX compliant fsync. Int fsync, int fd, open brackets. Oh, what comes next? Return 0. What do I do now?
Don't you have to set Verno to 0?
Because everyone always gets everything right in POSIX and implementation. The close bracket, if you miss that out, you'll have a bit of a problem. Probably not be POSIX compliant. And so you run this through GCC, and you get this, which I'm sure could be optimized a little bit more, and I'll buy anyone a beer or beverage of choice if they like optimize it within 3 seconds. I owe you a beer. So this is a tale of a really fast database server. A while ago, like pre-MySQL 4.19, so like don't like cry about your data going away. There was seeing some corruption of InnoDB pages. Sometimes. Only on Mac OS X. Also, things seemed a little bit faster than what you'd expect them to be. So it turns out that Mac OS X fsync doesn't flush the drive write cache. So
It doesn't always on Linux either. You sometimes need msync if you've been using mNow.
good point. Just to make it trickier.
We got trapped by that. People complaining about corrupt databases in XAMPP and eventually discovered that fsync was not actually syncing to this. You need to call both fsync and msync.
Interesting one. It creates it trickier with the cornea cases, and it's scary that like I've done enough research and I still didn't realize that one.
I still don't know which you're supposed to call first, fsync or msync.
So Tridge doesn't know. What kind of prick is making this software?
Variant of msync you call.
This is from user space code, so it's whatever the C library is cooling down to.
So like with SMP and you get it running exactly the same time, yeah, that's never going to cause problems. So they provide an extra F control to do this. Standards are great. Everyone has their own, implements them in different ways. Makes application developers difficult, like life difficult, and makes us want to like drink heavily. So let's see the InnoDB code for ensuring that data is synced to disk. If this doesn't work, transactions don't work. Recovery doesn't work. So it's a little bit of a critical bit of code when people like really want to run like their social networking site seems to be cool these days on it. So this isn't the code that syncs to disk. This is the code when you start up in ODB to check what it should do. So if we're on Darwin and we have fsync, then we're going to set a variable to say, yes, we do really have full fsync, which means we've compiled it on macOS 10.3 or later, because there's like this binary compatibility thing. So otherwise, we've compiled it in like macOS 10.2 or earlier, and we now want to determine if we're running on 10.3 or later. So, like, you call uname, then you do a strcmp, and then, like, there's an error case of, making transactions unsafe. Oh, and, like, you do ndif and stuff. So then you have, this is in, like, the sync call in, like, the OS compatibility layer, where you go, well, if we're compiled, like, before we had fsync, then we, like, steal the define out of the header file, and it's hopefully that's the same. Then we sort of, like, check if there is an ABI incompatibility, and like hopefully Apple never changes that, or someone's going to cry. So like if we have full fsync, then we sort of do something, and else we do the F control that then flushes the drive thing out. So this ends up having, like, macOS 10 has the slowest way to sync data to disk out of anybody, or at least slower than Linux, so all relevant operating systems. Otherwise we can use fsync or data sync, or just call fsync at the end, and who's crying? So you should write this code every time you actually do call fsync. If you're
Or someone could write libsave.
libsave, yes. Libsave.
How about call it libsane?
Libsane. Lib unfuck, really.
Lib e-kill POSIX.
E-kill Apple. So some OS vendors do hate you. So thanks to all the permutations for reliably getting data to the disk platter, we haven't even looked at like Windows yet, which seems to be a pretty small area of code. So like, yay to Microsoft. Big files, back to something that's just like making maybe performance suck. Writing to temporary file, sync and rename works badly on large files. I want your disk. So, especially if it's frequently modified large files. Like doing a couple of gigabytes of I/O generally takes more than a second. Pick the people who work for Silicon Graphics. Gigabytes of I/O a second? I piss on your memory bandwidth and do it to disk. There's actually a funny story. I was talking to a game developer mate of mine and saying when you recently got the XFS doing like 10 gigabytes a second of disk I/O, and he goes, fuck, we don't even get that memory bandwidth on the PS2. Goes and cries. So, frequently modified large files, you may want to start like redo and undo logging. Like for a database like Tablespaces, we don't actually like write to a temp file and rename. We do like logging, and you can do other neat tricks in there if you're like a little bit insane. So there are other cool tricks to do. Or not care so much. If you're ripping a DVD off there, I mean, there's a pretty good failure mode. It didn't work, try again. Downloading from the web or something, you don't really need to care too much about that. Video software, some of it saves like frame per file. One of the things is it can be easier to like do an operation on a single frame and like get some good known consistency semantics and like make clustered file systems cry. Large directories. So traditionally a directory is stored on disk as a list of name and inode. Is this ordered? So what kind of search operation are we doing? So that's the best like thing possible, right? Like you look through an unordered list from disk. So lookups are searched through the list, and typically allocation of disk space to directories is done like block at a time. Or if you're lucky, there's like batching foo. And so if you have like really slow growing directories, like add like a file per hour for like years and stuff. Actually, maybe not hour, per. What's the flush interval these days? Maybe a file every 5 minutes. You end up with a large directory with it's probably heavily fragmented.
Depends on your file system.
Yeah, it depends on your file system. So, like what lots of people use. Directory indexes help. Some are better than others. Make two file systems, x3 with dir indexed, and one with XFS. The XFS is faster out of the box, even when you write in order stuff out, like just in a for loop. By how much, whether you're going to care, hey. You can't always control the file system. So don't like assume everyone's going to be running the same file system as me on good hardware. So count of over a few thousand files being slow. Maildir is a very interesting application for like performance, especially when you consider the I/O thing of like listing every message, open, read, close. So where is data after it's been written? Transactions in databases are often committed, but not only written to the log. Only written to the log, not the main data file, right? So you could easily write a whole bunch of like metadata operations to the journal on the file system that if you crashed at that point, you'd replay them. So it's the same with file systems. So don't rely on reading the raw disk of like a mounted file system. Grubs had some problems here. It harms kittens. And if you don't think kittens are cute enough, it harms puppies. It does not lead to hugs and puppies at all. And in fact, it does hurt babies. Because they're going to grow up without like having a software that works. So there is a program called SQL Lite. Many applications have structured data that can be like easily represented in a SQL database. SQL Lite is ACID. D for durability, capital D. It's about a 200 kilobyte library, so it costs like essentially nothing. It takes a lot of the hard work out of things. FSpot uses it. Track. Some wikis can use it. Zernal or something uses it. Firefox is now starting to use it as well. So you can get a bunch of things pretty easily. And it turns out that like doing simple SQL in the application is pretty easy. And you can like, alter table and do funny things to upgrade your schemas. It's not so good with many clients reading and writing. It's brilliant for like document formats and maybe FSpot database for photos and stuff. It scales up to a few dozen gigabytes of data. It doesn't do like temp file and rename, it does like foo. So at that stage, when you get to a few dozen gigabytes, they say you probably want to use something that's a bit more heavyweight. So consider SQL Lite if you want to do something simple. Performance of large files, this doesn't so much eat your data as make performance sometimes a bit suck. So once in core on Linux, like the page to disk location is cached. Other OSs may vary, but this gets you a lot if your data set fits within the cache of main memory. The performance difference is in initial lookup, which you may or may not care about. Extents-based file systems are much more efficient at like at recording this and doing the mapping. Zeroing out a large file takes a long time. So if you're like create tablespace in a database, which is something we do, amazingly a lot when you're running test suites. Support for unwritten extents works really well. So a flag in an extent to say, when you read from this extent, give the application a 0 page. When you write to this page, flush that to disk. Simple little flag thing. Create tablespace. Running a test suite that's going to create a tablespace of like 4 terabytes or something. That's a lot of like I/O to flush out to disk. Also, like think BitTorrent. BitTorrent does a lot of like random writes slowly. So with unwritten extents, this can make what we call, fragmentation up the wazoo. So doing some like pre-allocation of saying, no, really, ditch my space on disk and I am going to write on it. So like we don't need to write zeros to it first and then write the actual data. That seems a bit silly. So this can help in applications like that. So this is how like old like Unixy stuff looks, where you have like list of some blocks, then you have another list of blocks and lists of blocks with the blocks. Extent, start list block, start file block length, and flags. That's a nice thing. You can like have 1,000 contiguous blocks pretty easily represented with not much data. Of course, you can have parallel threads writing files out. It's not uncommon to compete for disk allocation, especially with OSync, which just so happens about every database server in the world will always open everything with OSync, except apparently the original Unix port of Oracle. So files can get interweaved like AB, 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 which turns out to be pretty efficient when you're flushing out things, but not so good for reading. Extent-based file systems suffer because they're storing like 2-3 times as much data as a single block number, which can get a bit icky. And reading performance suffers. And with slow-growing files, generally like any pre-allocation kept in core may not be there, or like over reboot's not going to be there. So slow-growing files can be a bit of a problem area. So these are things to watch out for. Pre-allocate disk space. There is no standard way to do it. that works. So you can say that I'm going to have this table space that's a gigabyte in size. Please give me a gigabyte of contiguous disk space.
You're in trouble if you're on top of a compressed file system, because this many zeros and a whole lot of random data.
So a thing about MySQL cluster is we have this like pseudo real-time capability. We like to do things in like pseudo real-time. So it turns out that futzing a lot with extents and like unwritten extents and like futzing things out is something we don't want to rely on too much. So we do actually want to write zeros to everything. So pre-allocation, often a file system will do it for you. That's a great optimization. Thanks, guys. Doesn't work so well with OSync. There is no useful standard way to pre-allocate space. POSIX allocate doesn't work. Not that anyone really knew about the existence of this, but then you go and read the libc, the glibc implementation, which is literally like, let's write a zero. Next block, write a zero. So it's like for everything, write to zeros. XFS control for files on XFS that works like on IRIX and Linux when your file system is XFS. There is something on the classic macOS and the carbon layer from macOS, but nothing else that I can find in Apple's documentation for doing it. So the classic macOS is actually more advanced than macOS 10 in this area. So tablespace allocation in NDB. So in MySQL cluster, this is like copy and paste it out. We go, right, if the file is on an XFS volume, then we like print something out to let them know we're going to use something optimized. We say how big it is, call the F control, and then we use POSIX allocate to actually write zeros out to everything. So its implementation is about as efficient as ours. So this ends up with a continuous file on disk full of zeros, which is nice. Improvements. So you think, well, that's nothing special. So when you run the test suite as a developer on your laptop, which is like a nice busy file system that like constantly fills up because disk's nominal state is full, and you run the test suite all the time, like before pushing code, before checking in code as tests for everything. So it's not an uncommon thing to do. And we have like a bunch of tasks that do disk data creation, which involves running multiple cluster nodes on one machine, each creating out files that have all zeros in it. And all I owe is OSync because we're like paranoid up the wazoo. And like, what do we do when we create tablespace files? Like create, drop, all that kind of thing. So the number of extents for files, so when you're looking while the test suite's running, before this code was like 57, 13, 200, 95, 17. Create like gigabyte-sized tablespace and it goes up to like 1,000. With this code, everything's like 1 or 2 extents on my file system that has about a gig or 2 gig free. And this is for like small files, like 10, 20 meg. 30-second reduction in test execution time. I have like the MySQL test run numbers to prove it. I was, shall we say, even surprised that it was this much. So to get around sort of these kind of limitations, a lot of the developers actually run all their test suites on like the dev shum, isn't like on a RAMFS. So it turns out then your sync for your database actually just like writes to memory, and it writes really fast. Not so persistent storage over reboots, but like it runs pretty quickly. So library developers, no problem cannot be solved by abstraction, except when it's shit. So I'll pick on like the product I hack on, and this is the one bit of our like operating system abstraction layer that really pisses me off. The mysys, which is our abstraction layer, mystat returns like a mystat pointer, which is like assumed to be the same as stat, struct stat. POSIX stat returns an int. It's dead, so there's a problem there. You're trying to remember the semantics. And my fstat versus POSIX fstat, which does things differently in memory allocation stuff, and you end up like having, what have I found? Probably 3 bugs in the MySQL code related to this. So if you're going to make an abstraction layer, pick like somebody's idea of what the calling semantics should be and make everything look like it. Yes, here. There is hope. You can do file I/O correctly. It has been done, at least in a way that makes it really, really, really rare to lose data. You can prevent data loss, not just by saying backup every hour, just in case. You can pester people to make life easier, especially here. Good luck. Like, no one seems to know the entire semantics of everything, so good luck. And please don't eat my data. It makes me cry. Thank you. So I don't know if we have any time for questions, answers, or constructive abuse, violence even. But do we?
We've got time for a couple of questions.
Cool. Tridge.
Why are you using OSync?
OSync.
I mean, to give you a warm fuzzy feeling, make it go slower?
Yeah, so it is a warm fuzzy feeling and it does probably make it go slower, but it happens in more deterministic time if we decide when things get flushed out.
But it's not atomic. It doesn't give you any of your durability guarantees.
Yeah,
And
so
it will make things slower because fsyncing at the end allows it to do much better scheduling. So it just seems to be a warm fuzzy, but not much more.
so we do it especially for like writing out like undo logs and other miscellaneous files around the places.
Phase on that.
I believe we also do. It's just so.
And why do you need the OSync?
It's basically to also know when we're going to flush things out to disk. So we do a bunch of things that trying to guarantee the exact rate that we write things out to disk in, so that you're never going to overwhelm either the OS or your actual physical disk for writing things out. We literally have a configuration parameter which is megabytes per second worth to write out, and we won't go above that. And there is actually an error that a temporary error that returns that says wait. Ah! Let's go left to right.
Do you know of any file APIs that maybe like Play 9 or something that isn't as broken as POSIX?
So that would be cool if anybody used it.
Yeah. No, I'm just saying, do you have any experience with any file APIs besides POSIX that are not broken?
There are interesting things with persistent operating systems, but like not in widespread use, and probably are broken because most of them like experimental and barely used it. So the answer is no, there's nothing that's not broken.
Any alternatives to disabling write cache, like write barriers are working or something?
So write barriers are like getting to work, I understand, like with XFS is even using them now.
Express uses VSP3 can use them, Riser can use them.
Yeah.
Does XFS
Except if you're using LVM.
The write cache on there.
Every log write, it's a barrier write in XFS. So the last thing it does with an fsync is flush the log. So all the metadata is in the log. So yes, it does.
So it works on XFS and Riser, and everything does the right thing.
I have a quick comment. Actually, for what you shown earlier, how to rename the file. First save the file and rename the file. On Linux, you actually have to fsync the directory afterwards, because otherwise there's no guarantee that your rename has hit the disk. But there's no portable way to do this. In Linux, you can do it by opening the directory and then fsyncing it and then closing it. But you can't do it in any portable code, because at least in most of the BSDs, rename and stuff like this is synchronous. Traditionally.
So I have these couple of slides in there it's all about syncing the directory as well. So I had a couple of slides about syncing the directory and stuff, and I thought this is a really good exercise to see if anyone picks it up, and B, to have a long amount of time debating whether you should or not. And you could also have the semantics of whether you really care about that, like your semantics may be okay if it was the last version and stuff like that. So it is a good argument whether you should sync the directory or not.
Or you could just use the out options for XFS that makes all the directory operations synchronous.
Yeah. Or you can do like metadata synchronous now.
We'll have to cut her off there, I'm sorry. It's time for break and the next speaker will be coming up. Thanks very much.
So hopefully you're better in
Been getting handed to the phone. Right. Yeah, something. Something